Hello. Today in Applied Calculus we're going to learn about definite integrals. So previously we learned about indefinite integrals, and now we're going to see what a definite integral is. What we are trying to do is to find the area between a curve, a function, and the x-axis from an x value of a to an x value of b. So previously when we've done areas, we had some sort of formula, like the area of a triangle or the area of a rectangle, and we had a nice formula because that involves straight lines. When we involve something curvy that's not just a circle or something like that, then we're going to need calculus. So what is a definite integral? You're going to see the notation looks similar, but previously our integral sign did not have any little numbers on it. Now it will. And so we have to have a continuous function. We're going to have some interval from x equals a to x equals b that we are trying to find the area between that function and the x-axis. And so the notation will look the same. We still need the dx to say what variable we're using. But again, we will have the a and the b, where the a is the x that starts the interval that you're looking at, and the b is the x value that ends the interval that you're looking at. And what we're going to see is that this gives us the cumulative sum of the signed areas between the graph of f and the x-axis from an x of a to x of b, where the area above the x-axis, for instance here at b, is given a positive sign, and any area that's below the x-axis between the function and the x-axis is given a negative sign. And so what we're going to get is net area. So any of the negative and positive that counteract each other, and then we see our sign. So if the sign of one of these is positive, it means that there is more area above the x-axis than below. If the sign of one of these is negative, then there's more area below the axis than above. And so that function inside is still called the integrand, and now we have these numbers where the start of our interval a is the lower limit of integration, and b is our upper limit of integration. So here we have the function y equals x squared. And you can see the shaded area is going to show us the area we're referring to here. So we are looking between the function and the x-axis. Currently, I have our interval as x equals 1 to x equals 3. So what we're going to be looking at is basically thinking about sweeping out an area and seeing what that is. So think about if you watch the weather, of course that's going around in a circle, but as the radar line goes around, you see it update and show you where the clouds now, right? So it's sweeping out an area as you look. So watch as we keep A where it is and we sweep out an area by letting B move to make a bigger and bigger interval. So see how we get more and more area as B grows there? That's the idea, is that we're accruing area as we let B change. So we're going to use this idea to figure out areas. Here we are just applying basic properties of these. We don't actually know how to evaluate one on our own yet, and we won't until the next section. So we have to be given information about the different areas at this point, and we're just using properties. So we know the different regions, but remember, anytime an area is above the axis, we will count it as positive. Anytime the area is below the axis, it will be negative. So for a problem like this, they've given me the areas that I have, and for part A, I am going from A to 0. So I'm starting at an x of A and sweeping out the area that I get until I stop at x equals 0. That is region A, big A, that I have swept out. They tell me that's 2.33, but it's below the axis. That's all. That's the whole problem. All right, let's look at another one. So this time we're going from 0 to B. So we start at an x of 0, and we sweep out the area until we get to an x value of b. What we see is that we have covered the region capital B, and we know its area. Also, it is above the axis, so I simply write its area. That's the answer to the question. All right, don't make these harder than they are. The last problem here is 0 to c. So this is going to be a little bit different. If I start at 0 and go all the way to c, I have passed two regions. One the capital B, one the capital C. So from 0 to B, we just did that. We got region B, and that was above the axis, so it was 10.67. Then from B to C, we get another region, region capital C, but it is below the axis. So since it is below the axis, then we could think of it as plus a negative or minus, right? That I'm adding that area, but that area is below the axis. So since this actually gives us net area, we're going to say negative. And so the positive and the negative area will cancel each other, but we can see there is more area above than below, and so we will get a positive answer of 5.04. So that's all you're doing for these, is looking at the areas given and remembering that any area below the axis will be counted as a negative because this gives us net area. So these are some other properties. One we actually just used, but remember, if we are using this as a slider bar and accruing area as we change what the end point is, then if we integrate any function at all from A to A, if we start and stop at the same place, then we have not swept out any area at all. And so the answer is 0. So if you see a homework problem that looks like something you've never done before, that the function's too complicated for you to work with, pay close attention and see if it isn't just a moot point because the upper and lower limits of integration are the same, and so the answer is just 0. All right? Another one that we're going to have to think about, we've always been sweeping out from left to right. If our upper and lower limits of integration are not such that the lower is smaller than the upper, which is what we're used to seeing, then we might need to use this rule. So if these are not in the usual order, or they're not in the order of what you know, and we'll see that in a second, if we flip them, so this was A to B, if we flip it now so that it's B to A, then we get a negative sign. So look out for that and be careful. What you would do as a first step is flip it to the way that you need it and put that negative and then proceed. C, it turns out that a definite integral is actually defined formally by a limit. We're not having to go into that here, but it is, and we had all those limit laws. And so if you have a constant times your function, you can bring the constant out in front and then evaluate the definite integral. Also, if you have the integral, definite integral of the sum or difference of two functions, you can take the definite integral of each one individually and then add or subtract them. So we saw that with limit laws. We saw that with derivatives because a derivative is a limit. We saw it with indefinite integrals because that is connected here and is also a limit. And then we just used number 5, actually. So if we need to integrate all the way from A to C, then depending on the information we have, like in that last problem, we may need to break it up. We can integrate from A to B of the function, and then notice this is the same function here, and then integrate the rest of the way from B to C. So I'm simply breaking the area into two pieces, that piece and this piece, and putting them together, and I will end up with the answer that I need, which is that sum of that net area. So you could be asked questions like the first one we did. Again, all we have is these properties, so you have to be given information. You have to either be given a graph with the areas known, or you have to be told the answers to some of these definite integrals at this point because we don't know how to do it ourselves, but we will in the next section. So these are the only facts I know. So if I'm asked anything else, I have to use the properties we just discussed to rewrite them so that this is all I'm using. So for instance, in part A here, I don't know anything about 6x squared dx integrated from 2 to 3. I only know about x squared dx integrated from 2 to 3. So I need to get that 6 out of there. But we have a property that says that if you have a constant inside, it can be taken out front and then multiplied by the result. And so that's exactly what we'll do. We'll rewrite it as 6 times the integral that we do have information about. And then I was told that the answer to that is 19/3. The integral sign and everything is gone because this is the answer to it. So that's going to be our big difference here. An indefinite integral, the answer had x's in it and a plus c and was a family of functions. Here with a definite integral, it represents an area. There is a definite region we're looking at from x equals a to x equals b, and so we are determining an area. The answer to these are going to be numbers, so keep that straight. So now I say 6 times the value that I was given, and I'm able to get the answer of 38. Now here you can see that I have a difference of 2 and I have constant multiples. So at first I can break it up into 2 separate integrals of each of the functions, right, with subtraction in between. They do each need their own dx. Then I can bring any of those constants out in front. Then I have integrals that I was told about. So 0 to 2 of x squared dx I was told is 8/3, and 0 to 2 of x dx I was told is 2. I plug in those values and get the answer. So 9 times 8/3 minus 4 times 2, and work it out and get 16. That's all there is to it. You're really just plugging in values that you know after you apply those properties. So a couple more here, same definitions that we had before. And so this one I need to be really careful of because I don't actually have any information about 2 to 0. So I know they're the same numbers, but the order matters. These are both given as 0 to 2, and specifically I see I'm dealing with a regular x. So the very first thing I need to do is flip the order so that it is close to something I know about, and when I do that I get a negative out in front. Okay, so I have a negative out in front, and now I do have the order 0 on the bottom and 2 on the top, the lower and the upper limit of integration. And then I'm integrating 3x dx. Well, that 3 is a constant that can come out in front. And now I have negative 3, the integral of 0 to 2 x dx. And I was told what the integral 0 to 2 of x dx was. It was 2, so I simply replaced that with the answer. And now we have negative 3 times that answer of 2 and get negative 6. Okay, so very first thing, flip it to make sure the order matches up, and that gives you a negative sign. Then proceed as we've done before. Now this one, we do have information about x. We could take the 3 out, but before I even get that far, I don't have any information where the limits of integration are negative 2. This must be a trick question, but Professor Palm doesn't ask trick questions, right? So there's something up. I only have this information, and so how do I answer this? Well, no area is accrued. I start at an x of negative 2 and I end at an x of negative 2. I did not sweep out any area. So it's okay that I have no information about a limit of integration involving negative 2 because the answer to this problem is 0. Okay, so do look out for that. So the answer is 0 because no area is accrued if you start and stop sweeping out your area at the same point. Okay, so let's look at one more of these. And what you'll notice with this one is our limits of integration are 0 to 3. Now, none of the information I have has limits of integration of 0 to 3. I have 0 to 2 and 2 to 3, and we've talked about a property with that. So I'm going to integrate from 0 to 2, and then the rest of the way 2 to 3, right? Think about the number line. If I just add those two, the areas under the curve, under the function, between the function and the x-axis from 0 to 2, and then the area the rest of the way from 2 to 3, then I'll have the total area. So I'll break this into 2 pieces. The integral from 0 to 2 of 12x squared dx plus the rest of the way from 2 to 3 of the same function, 12x squared dx. Then both of these have a constant 12 that can come out in front. And now we have information that we do know. We know about 0 to 2 of x squared dx. We know about 2 to 3 of x squared dx. We simply plug those values that we were given in, and then we are able to compute the area. So what we've seen is you have to, at this point, be either given the picture of a graph with the areas designated or be told the answers to some of these definite integrals. And you're always just using that idea of area and net area. That area below the x-axis is going to be negative and area above will be positive. and those properties that we learned about these definite integrals. So the last thing I want to do is compare and contrast, because we first learned indefinite integrals when we first learned about antiderivatives, and now we have definite integrals. And the answers and everything are different, and we need to take note of that and know what to expect. So an indefinite integral, remember, had an integral sign with no numbers on it, no limits of integration, because it was indefinite, okay? Now the answers to these were functions. In fact, they were whole families of functions, which is why there was a plus c. So it was a function, it still had variables in it, and we had that plus c because that actually was the whole family of functions. On the other hand, a definite integral does have little numbers on it. Those are those limits of integration to give us the definite area that we're talking about. And here the answer is a number. So you will not have any x's left. You also will not have a plus c. So you could have a multi-part question where one of them is an indefinite integral and does not have little numbers on the integral sign, and its answer is that antiderivative function that still has x's and a plus c. And then in part B, the very next part of the same question, you could have it look almost the exact same, still an integral sign, still a function, but have little numbers on it. That means you are dealing with a definite integral, and while we don't quite yet know how to evaluate that ourselves other than through properties or given information, we will know how to after next section, and that's going to be a different process, and we will not have a plus c, and our answer will be a number. So keep that on your radar as you're practicing, so that when they're all mixed together at the end, you're able to tell the difference between them. So next section, we'll be able to learn how to evaluate one of these definite integrals on our own without having to be given graphs or property information to be able to fill in.